Here's a fact that should scare you a little. A single bacterium splitting every 20 minutes with nothing to stop it. In about a day and a half, its descendants would outweigh the entire planet. Nothing in nature actually does that. So the math that predicts it must be missing something. Let's find out what. Let's start simple. Call the number of individuals n, and let it change with time t. Rabbits in a forest, people on Earth, bacteria in a dish, same question every time. If we know how many there are now, how many will there be later? Over a short slice of time, delta t, two things happen. Some are born, some die. And here's the key assumption. Both are proportional to how many there already are. Twice the population, twice the births. So the change is a birth rate minus a death rate times the population times the length of the step. Births minus deaths, we bundle that into one number, the growth rate, p. Now shrink the time step down towards 0. That ratio on the left becomes a derivative, and we land on the cleanest law in all of population biology. This is Malthus's law from 1798. And it solves in one line. The rate of growth is proportional to what you already have, so the population grows exponentially. N of t equals n naught times e to the pt. And this little formula already tells two stories. If the growth rate is negative, more deaths than births, the population decays to 0 and dies out. But if it's positive, it climbs and climbs, faster and faster, with no ceiling whatsoever. Forever. And that's exactly the problem. Because no forest has infinite grass, no dish has infinite sugar. Real resources run out, which means the growth rate simply can't stay constant. At some point, the crowd starts to fight over the last of the food. Here's Verhulst's fix, from 1838. Don't treat the growth rate as a fixed number. Let it fall as the population fills up. When n is tiny, the rate is at its full value, r. When n reaches the carrying capacity k, the rate drops all the way to 0. Draw a straight line between those two, and you get the growth rate as r times 1 minus n over k. Now plug that shrinking rate back into our growth law. And out comes the logistic equation. The change in n is r times 1 minus n over k. Look at what that extra factor does. While n is small, 1 minus n over k is basically 1, so it grows just like Malthus. But as n approaches k, that factor melts to 0, and the growth quietly shuts itself off. Solve it, a bit of partial fractions and one integral, and you get the famous logistic curve. It starts off looking exponential, races upward through the middle, then bends over and settles gently right onto the carrying capacity k. And here's the whole story in one picture. Malthus and Verhulst start out identical, the same steep, hopeful climb. But then they part ways. Malthus keeps going straight off the top of the world. Verhulst remembers that the world is finite, and comes to rest. Strip away the numbers and the logistic law has just two resting states. 0, extinction, which is unstable. Nudge it up and life takes off. And full capacity, k, which is stable. Push it either way and it always drifts back. So from any positive start, the population marches to k. Every time. So that's the difference one honest factor makes. Malthus gave us the explosion. Verhulst gave it a memory that resources are finite and turned a runaway into an S. The exponential is the dream. The logistic is the world we actually live in.